record this. I record all these sessions and it'll be posted on the same channel that they were always posted on, my Digital Math Tutor YouTube channel.
Okay.
What do you got that we can start on here?
Hold on. I think I left it downstairs. Let me just go grab it.
Uh-huh.
All right. Sorry about that.
All right. I just walked in the door and it gave me a chance to go change into comfortable shoes.
Okay, so we'll start with this one, I guess.
Okay.
So it's just taking the derivative.
Uh-huh.
And it's going to be 1 over 1 minus 2 cosine x.
That it?
Yes.
Okay. We can't do much with that. We can't really split it up. I suppose I could simplify it a little bit so that we wouldn't have to use the quotient rule, but the math I would have to go through to simplify this wouldn't be worth the time in order to get it all in the numerator. And I might still have to use the quotient rule. So let's just go ahead and use the quotient rule. What is the quotient rule? Do you have a way of memorizing it?
Not really a way to memorize it. It's just
Let me help you. I got a perfect way to memorize it. If a function is the quotient of two functions that are both functions of x, then f prime, you only have to remember one thing. Starts with the bottom, ends with the bottom squared. What could that mean? Well, if I start with the bottom, the term next to it must be the derivative of the top. Order matters, so it must be subtraction, not addition, like the product rule. And the other two terms must be the reverse of that. So it must be that times that, all divided by the bottom squared. That's the easy way to remember it. Starts with the bottom, ends with the bottom squared. Everything else you can figure out what it has to be.
Okay.
Okay? So, let's do it with this function. Let's start with the bottom.
Okay, so we got, I always forget the trigonometric
Well,
how to
just start with the bottom. We're not starting with the derivative of the bottom. We're starting with the bottom.
Okay, so just 1 minus 2 cosine x?
Yeah. Times the derivative of the top.
It'd just be 0.
Minus the reverse. So it's the top. And now the derivative of that denominator is what?
So the 1 would be a 0.
Okay. What's the derivative of that?
Would you have to do product rule for that?
No. That's just going to be negative 2 sine of x.
Okay.
Okay. So the negatives cancel out and you end up with 2 sine of x. Because I end up with, when I take the derivative of that, I get negative 2 sine of x. So I have 1 minus a minus, which turns into a plus.
Right.
All over 1 minus 2 cosine x squared. And you don't necessarily have to do that. You don't actually have to expand that. Notice that term goes away. And so I still have a minus in the numerator. I actually I had 3 minuses. In other words, I had that minus right there. And I had this minus right here, which is a different minus. And then when I took the derivative of cosine, I got minus sine. So I do have three negative signs, which combine to make this single negative sign in the numerator. It's all over this. And actually, no, I was going to say, might be worth squaring that, because we might end up with a 1 minus cosine squared, which is an identity for sine squared. In other words, if we could turn that into sine, then I can do some simplification.
Right.
Let's see. I don't think it does. Here's what we end up with. If we multiply the bottom, you get 1 minus 4 cosine x plus 4 cosine squared of x. And I see nothing about that that would allow me to substitute anything in the way of sine. It's not like I have a 1 minus cosine squared. If I had that, then I substitute sine for it, and then I can cancel out some of these signs up here. Thinking
Do you know what?
Any other identities, if there's any other trig identities that looks like, it actually, if that was squared there, then that is the identity for the cosine of 2x. But that doesn't really help things. Having the cosine of 2x, I would not be able to simplify it. Even if I could replace the bottom with cosine of 2x, it wouldn't help. And I can't because that's not squared. The square is outside the parentheses. So by the time I square this whole thing, I get this over here, and that doesn't allow me to simplify anything. So the better answer really is to leave it like this, what I have circled over here on the right.
Okay. Do you have a good way to remember the derivatives of like sine, cosine?
I do. I have a great way to remember it. Let me go through it with you, because I noticed that gives everybody problems.
Oh yeah, definitely.
Well, this will help. You got to memorize some of them. Derivative of sine?
Negative cosine.
No, positive cosine.
Oh, that's right.
The next one to memorize is tangent. Let me tell you one way to not memorize stuff. Don't look it up.
Okay.
You're going to have a better chance of memorizing it if you guess and you're wrong. What do you think the derivative of tangent is? At least when we're working in a session. Obviously, if you're doing homework and you have to know what the derivative of the tangent is and you don't know what it is, you got to look it up. But if you're attempting to memorize something, you don't always want it on a piece of paper in front of you. Because what I found is that everybody invariably looks it up and it never gets memorized.
Right.
The only way to really memorize something is like with flashcards, where you have it written on a flashcard and you turn it over and you try to, on one side you have the function, on the other side you have its derivative, and you just practice. But this is a hard one to memorize right here. The derivative of tangent is secant squared. And the last one that you really have to memorize is secant. And the derivative of secant is secant tangent. Okay? So memorize that, and that. And then I'll show you how to get the other three easily. You're familiar with cofunctions. What's the cofunction of sine?
Cosine.
What's the cofunction of tangent?
Cotangent.
And what's the cofunction of secant?
Cosecant.
Okay. So if we look at the cofunctions and we want to know what the derivative of cosine is, first of all of our cofunctions, the derivative is negative. Okay, so I'm going to put it inset a little bit. I know that's a negative, I know that's a negative, and I know that's a negative. You with
Right.
me? Now, what is the derivative? It's the whatever the cofunction of that is. Well, the cofunction of cosine is sine. So those two go together. What's the cofunction of secant squared?
The cosecant squared.
And what's the cofunction of each of these, the secant and the tangent?
Cosecant, cotangent.
And there you go. There's
All
your
right.
derivatives. Notice that you don't have to memorize these. You can always figure those out. They all begin with negative signs, whereas the derivative of the trig function that doesn't have co in front all begin with positive signs.
Right.
But you do have to know that the derivative of sine is cosine. That's pretty easy to memorize. Usually when they teach it to you, they teach you this number one, and then unfortunately they teach you that one as the second one.
Yeah, that's how we learned it.
That's how all calculus teaches it. And unfortunately, it doesn't really clarify the pattern. In other words, you don't know. It makes it look like the derivative of sine is cosine, and the derivative of cosine is sine because they're opposites. It's not that. It has to do with the cofunctions. So a better way to teach it would be to teach you that one, and that one. Say memorize those three. And then the other three you can always figure out.
Right.
The secant is not that strange because the answer includes secant, the word secant on it. So secant being secant tangent, it's fairly easy to memorize. This is probably the toughest one right here, memorizing that the derivative of tangent is secant squared.
Right, yeah.
Okay, so I'm going to take this page, I'm going to scroll down, I'm going to test you. And don't have anything in front of you that has these on it. If you've got something on a piece of paper, turn it over.
Okay.
I'm going to give a function, you tell me its derivative. It's always tangent of x. In other words, you always need an argument. You never have just tangent. It's always tangent of some variable.
Right.
Sometimes I'll leave it out just because that's not the important part. But what's the derivative of tangent?
It's secant squared.
Yep. What's the derivative of sine?
Cosine.
What's the derivative of secant of x?
Secant tangent.
So you got them all memorized already.
All right.
Now, what's the derivative of cosecant of x?
Negative cosecant cotangent.
Good. You definitely have the pattern memorized. What's the derivative of cotangent of x?
Cosecant squared, or negative cosecant squared.
Perfect. You got them. That's it. The only other ones that are super important for you to memorize are the derivative of natural log. In other words, if y equals natural log of x, what's y prime?
We did that just the other day and I forgot.
1 over x. And
that's right.
Quite unusual that that is the case. And
yeah.
Actually, an awful lot of much higher calculus is based on this. And this is what makes the natural log function so important in math, and it's also what makes the number e so important. Okay? So the other one is this one. What's the derivative of e to the x? It's the only function in the world that has this property. Its derivative is the same as it.
Oh, that's right, yeah.
There is one other function that has that property, and that's y equals 0. And the derivative of that is also 0. But that's useless. That doesn't help anybody. In other words, since that's a point, the way to really remember this is that is unique in the world. Only one function whose derivative is the same thing as it. So you need to memorize that, you need to memorize that, you need to memorize your 6 trig functions, and that pretty much is it. There are 6 inverse trig functions that you probably haven't gotten to yet.
No, not yet.
There are derivatives of 6 of those also, and those are a little more difficult to memorize, a lot more. But we won't go into those yet.
Okay.
What else you got in the way of specific problems? Because I think what we've talked about so far today will cover most any problem that you're going to give me.
Okay, it's another derivative one. It's derivative of the square root of x to the 5th.
Hold on one
plus
second.
2x. Okay.
Problems here, getting this thing to scroll down. There we go. No, it won't go below that. Wow, that is wild. Let me go up. Okay, go ahead. I'm sorry. What was it again?
The square root of x to the 5th plus 2x plus 3.
All right. 1 minute. I gotta figure out what's going on here. Let me work on this page right here. Hopefully writing won't appear. I'm sorry for a third time. What was it again?
That's okay. It's square root of x to the 5th plus 2x plus 3, and that's all under the square root.
Okay. How should... That's what I was afraid was going to happen. I'm going to have to close this out and reopen it. I apologize.
That's okay.
I hope that solves the problem. This program used to work perfect, but once I uninstalled OneDrive, it stopped working really well.
Oh, yeah.
OneDrive was screwing me up really bad, so I had to uninstall it. Now this program doesn't work very well. So it was y equals the square root of x to the 5th minus what?
It was plus 2x plus 3.
Okay. Radical signs don't work very good when you're taking derivatives, as you've discovered. So what's a better way to write that?
You could do all of that.
What is the exponent? What's the radical sign mean?
It'd be 2 to the 1/2 power.
Okay. Now, what are we going to use to take the derivative of this? Which of the 4 rules do we need to use?
You start with the power rule.
Correct. And what? Chain rule.
Yeah, that's right.
Okay. Chain rule is probably the most difficult of the 4 rules to wrap your head around.
Definitely, yeah.
The best way to look at the chain rule is to figure out what the inside is first. Okay? And even to the point of using a letter to let's represent what that inside is. What do you think the inside is here?
Just everything in the parentheses there.
Now, what's the chain rule say in a nutshell?
I believe it's the derivative of the outside,
and
then that's times just not the derivative of the inside.
No, that's it. It's very straightforward and very simple sounding, and that helps. And if you can remember that, then these will all be easier. The only difficult part at all is figuring out what the inside is. This is easy to figure out the inside. So let's differentiate it. Y prime, what's the derivative of the outside going to be? In other words, another way I can now write that is u to the 1/2, right?
Right.
Okay, so what would the derivative of u to the 1/2 be using just the power rule?
It'd be 1/2 u to the negative 1/2.
Yeah, and in place, I'm not going to actually use the u. I'm going to use what u is.
Right.
So, in other words, you don't ever change the inside when you use the derivative of the outside. That is the derivative of the outside. Now, what's the derivative of the inside, which is u prime?
That would be 5x to the 4th plus 2.
That's what I'm multiplying that by. And there is my answer. And it's always that straightforward. It's the derivative of the outside times the derivative of the inside. Now the chain rule, it's called that because you can have multiple chains. You can have multiple insides. In other words, let's say I had a function that had more than one inside. Then it's the derivative of the outside times the derivative of the inside times the derivative of that inside. You don't necessarily get ones that will have multiple chains, but just to let you know, it can be used multiple times. What's your next function?
Let's see here.
I want to make sure we leave enough time so that I can give you a couple, because I can give you ones where the inside is not obvious. And those are the... Try and give me some more of yours. Give me some that you think are tough, that you're not sure you know how to do.
Okay. This one I might have to send you a picture.
Okay.
Find y prime of pi where y equals the cosine of x.
No, this is fine. What they want, I'm going to call this f of x instead of y.
Okay.
There's a reason for it. The f of x notation is a little more powerful than the y notation. First of all, let's figure out what the derivative function is. What's the derivative of cosine?
Negative sine.
Okay. And now what they're asking is, what is the derivative evaluated at pi? That's what they're saying, right? That's what it says in your book? Basically?
Yeah.
Okay. So, what does that mean? That means minus sine of pi.
Oh, so all you do is just plug it into that derivative?
That's exactly right. Whatever is in the parentheses, this is a rule of mathematics. When you have f of x notation, whatever is in the parentheses gets plugged in for x. Or if you have f of t, whatever's in the parentheses gets plugged in for t. But the f of x notation is powerful for one thing. It tells you it's a function of x. It's not, you're not going to find t's or r's or any other variable on the other side. You're going to find x's.
Right.
Secondly, it allows you to evaluate either the function or a derivative at a certain value.
Right.
As with y, if I'd have used y, then I could have written y prime, but then you can't really write. I mean, you could do this, and people would understand what you meant, but that's y notation doesn't really allow for that, whereas f of x notation does. So that's why you'll see most of your functions f of x.
Yeah, that's probably why this
y anymore.
Yeah, that one's confusing because that's how it was written.
Yeah.
On here.
Okay. Got some more?
Yeah. This one here, this one says
now,
find.
I'm presuming that you're beyond the limit definition, the limit quotient definition, right? In other words, you're probably like every calculus student, they insist upon teaching you that first. You have to figure out derivatives based on the limit quotient definition, and that is brutal mathematically. Once you learn the power rule and the product rule and all four rules, that's the only way you ever do differentiation again.
So you mean the
I mean, the definition of first derivative is this.
With the f of x plus
that's
h.
the limit of f of x plus h
plus f of minus f of x
all over h as h goes to 0.
That's right, yeah.
That's the official definition. And if you have to do first derivatives based on this, they're like 10 times harder.
Yeah, we did have to do that.
You can do them, and the reason they're so hard isn't because of the calculus, it's the algebra. These turn into algebraic monstrosities. So you're sitting there doing tougher algebra than you've ever done. That's what makes it hard. But that is the official definition. And in fact, it's this definition that you can actually use to prove the product rule and the power rule and the quotient rule and the chain rule. All of them were derived from this definition. And so when I said you're beyond that, I want to make sure none of these problems are telling you you have to use that definition to come up with the derivative. We can do something like that if you are still doing that. But usually once you get beyond that, they don't go backwards. They don't make you go back and do problems based on that definition anymore.
Right. Well, we had one on our last test that was like that, but I don't think we'll be doing that again.
Probably the last one you'll get. You may get one on a semester final where you have to do one of those. And I'm happy to go through one of those with you if you want. But I'd say that since you're into the product, quotient, and chain rule, we should do some more ones involving the chain rule.
Yeah.
Maybe a couple, just because I know what I want to give
you. This one here is a little different.
Okay, go ahead.
It says find dy over dx by implicit differentiation.
Okay. Implicit differentiation is a whole new topic.
Right. And it's
go ahead.
2xy minus y squared equals 3x plus 9.
All right. When you explicitly differentiate it, the equation is solved for y, right? You have y equals, it's a function of x. That's explicit differentiation. When you have an equation like this, notice that I can't solve it for y. I got a y and a y squared. I want to see you solve that for y. So there's another technique called implicit differentiation, where you just start, I'm going to differentiate the left side of this equation and the right side. Okay?
Okay.
So here's basically what I'm doing. I am differentiating with regards to x, both the right side and the left side. That's what I'm going to do. And I'm going to end up with dy dx, which is what I want to solve for. Okay?
Okay.
Now, here's what you do. You differentiate just like normal, and if you come across an x, you do everything normal. But if you come across any variable that is not x, that is not this variable right there, in other words, if I come across a y or a t or an r, I differentiate it normally, but I follow it with a dy dx.
Okay.
Okay. For example, let me give you a little easier one here so that we don't have to worry about the product rule because that can be confusing. Let me scroll up so that I can write it. If I write this function right here, the equation of a circle, okay? And I want to implicitly differentiate this to come up with dy dx. Well, when I differentiate x squared, I get 2x. Don't have to follow it with a dx dx because that's 1. But when I differentiate the y variable, that's 2y, but since that's y, I got to follow it with dy dx. Now I differentiate the right side and I get that. Now notice that I can solve for that. I'm going to move the 2x on the other side, and I'm going to divide both sides by 2y. So I'm going to come up with this answer. Dy dx equals minus x divided by y. That's what dy dx would be. You see how when I solve this equation, I'm going to get that?
Yeah.
Okay. So that's implicit differentiation in a nutshell, is that when you run into a different variable other than the variable in your denominator, you have to follow it with dy dx, or if I'd have run into a t, I would have had a dt dx after it. Okay? Now, handle your problem, which is a little more difficult because it's going to involve a product rule also. So let's start with applying the product rule. And the product rule has a plus sign between the two terms, right?
Yeah.
Which means you can do it either order. You can do uv prime plus u prime v, or you can do it in the reverse. I've found that in tutoring calculus students, it's hard to know which way they're doing it. So I think it's a good idea to always do it the same way. In other words, if y is equal to u times v, then let's always make y prime, just always start with u, v prime, plus the opposite, u prime v. Just always do it that way, because usually what I found, what happens to students is they try to do whichever one is the easiest derivative first. And then it's very difficult for me to follow what they're saying. So let's always start with u. So what's u here?
Is it just 2 or is it 2x?
2x. That's what u is. And v is y. So what's v prime? Okay. So what's v prime?
Just be dy over dx.
Yeah, it's 1 times dy dx. In other words, I got to put the dy dx in there because I was differentiating a variable other than x. Okay? We're still doing the product rule on this term. We need the second part of it. In other words, we need this part. What's u prime v?
So it'd be just 2y.
And we don't need to follow that y with a dy dx because we weren't differentiating v.
Right.
Okay? So this is just the answer to that. Now, let's continue on. Minus what?
That would be 2y dy dx.
Yep. Now, I'm going to scroll down and rewrite this from the left. In other words, this is, when you're doing implicit differentiation, it's also some difficult algebra, but not as difficult. Okay. So here's what I've got so far. That's the left side of the equation. What was the original right side of the equation?
It was 3x plus 9.
Okay, so the derivative of that is just 3. And there's no dy dx involved. Okay? So now the goal is to take every term that has a dy dx in it, put it on one side of the equation, and everything else on the other. So I got two terms. So here's what I got. 2x dy dx minus 2y dy dx. And I'm moving that 2y to the other side of the equation. Okay?
Okay.
What would the next step be if I'm trying to solve for dy dx?
Be to divide that.
Think factoring.
Okay, yeah.
I can factor out a dy dx, right?
Yeah.
Leaving behind something the whole thing is multiplied by. And now I can solve for dy dx.
Okay.
I
just divide
both sides by that coefficient. Now you'll notice one very significant thing. When you do, and that got divided away. So I've solved for dy dx. It's equal to what I have circled. Now, the one significant difference when you're doing implicit differentiation as opposed to explicit is explicit always gives you an answer with just x's in it. Notice this answer has both x's and y's. And that's quite normal, quite common, and very okay. Because if I actually want to figure out the slope of the tangent line anywhere on that circle, I'm going to have an x and a y value. That might be 2, 1. Okay? So if I want to figure out the slope of that tangent line, then I implicitly differentiate it, solve it for dy dx. I'll get a function that has both x's and y's in it, but I'm going to evaluate it at a point where I have the x and the y. If I only have the x, well then plug in the x into the original function and you can figure out what the y is. But they'll give you both. On these implicit differentiation problems, they'll give you both the x and the y value as to where you're supposed to calculate how you come up with the slope dy dx.
So then you just would plug that into Jeff's circle.
Did this particular question ask you anything further other than just the derivative, or did they ask you to evaluate the derivative at a point, or?
I've seen questions like that before, but not this particular question.
Okay, well, if they wanted to know what dy dx was at the point 1, 2, then I plug in 1 for x and 2 for y. So I get 3 minus 4 all over 2 minus 4. So I get minus 1 over minus 2, 1/2 would be the slope of the tangent line at that point for this function they were given. In other words, if I were to open up Wolfram alpha and graph the original function or the original equation, it would show me something where if I looked at the graph and wanted to estimate the tangent line at 1, 2, it's -1/2, or it's whatever I got, +1/2. And you would see that on the original function.
Right.
Remember what derivatives are, and this is something that's really easy to forget. Derivatives are slopes. That's why for 3 years in math, you've been talking about slopes. Only the slopes you've always talked about prior to calculus are average slopes.
Right.
If I have a function and I want the average slope from there to there, then I take the rise over the run. That is, whatever the slope of that line is my average slope. Well, derivatives are slopes at a point. The rise is 0 and the run is 0. So finding derivatives finding slopes of tangent lines at a point is fundamentally difficult because it's 0 divided by 0.
Mm-hmm.
Why Newton didn't publish calculus when he first discovered it. He waited 25 years to publish calculus. And the reason is he didn't trust it. He didn't like this concept of dividing by 0. And you don't really divide by 0 in calculus. What you do is you divide by a number that approaches 0. That's kind of the essence of calculus, both differential calculus and integral calculus. It's all about dividing by numbers that are very, very tiny, that approach 0. But anyway, I mean, the story of Newton's really an incredible one because calculus is now called the greatest discovery in the history of mathematics in terms of changing our world. And he discovered it and he wouldn't publish it because he didn't trust it. There are mathematicians that went to their grave. I don't know if you've ever heard of Raleigh's theorem. Raleigh's theorem is the same as the mean value theorem. They also call it Raleigh's theorem. Well, guess what? Raleigh never accepted the validity of calculus. He went to his deathbed denying that calculus was a legitimate mathematic discipline. And they named a theorem after him, a critical theorem, one of the more important theorems in calculus.
Wow.
Which is kind of funny. It actually is rather amazing how many theorems are not named after the person that invented them, including the Pythagorean theorem. That was not invented by Pythagoras. Almost every math theorem was not invented by the person that it's named after, like Raleigh's theorem. He didn't have anything to do with inventing that. So, what else you got? We have 10 minutes.
I don't think we've done a real quotient. We had one that kind of had the quotient rule. Okay. This one's a more difficult one.
Yeah, let's do here, I'll use, if we're just taking the derivative, or are we going to have to evaluate it also?
It just says derivative.
Okay, then I'll use the y notation. What's the function?
It's x squared plus 3x, and that's over 7 minus 2x.
Yeah, this is a better one to do than the other one they gave you. Okay, so what's y prime? What's the rule? What's the quick and dirty way of remembering the quotient rule?
You always start with
begins with what?
With the bottom one.
And ends with?
The numerator.
No, ends with the bottom squared. That's right. It's so easy to remember. You only have to remember one word, really, the bottom. The bottom is key to memorizing. Begins with the bottom, ends with the bottom squared. So let's do it. Begin with the bottom.
7 minus 2x.
And we know we have to multiply that by something. What do we have to multiply it by?
The derivative of the numerator.
Okay, which is?
It should be 2x plus 3.
Okay. And now, since it was important that I begin with the bottom, we must not be adding here. Because if I was adding, I could have begun with the bottom or the top. So the fact that I had to begin with the bottom tells me that order matters, which means we're subtracting for the second term. Okay, now do the reverse. In other words, obviously these two need to be the reverse of the first two. So now take the derivative of the bottom.
Which would be just -2
times just the top,
x squared plus 3x.
all divided by what?
The bottom squared.
Right. And usually you don't want to multiply that out. You want to leave it like that. Frequently, you're going to end up with a term in the numerator that can cancel out one of these 7 minus 2x's. Not in this particular problem, but frequently. And so
Right.
you don't really gain anything by multiplying the bottom out. However, the top, we're going to be able to simplify that numerator quite a bit. So we do want to multiply the numerator out. I'll show you why here. Yeah, we got enough time. Go ahead and FOIL these two. What do you get?
So the 14x minus 4x squared.
When you FOIL it, you want to do it that, and then you want to finish with the 7.
Right, yeah, I tend to do
okay.
The first and then the inside.
I won't mess up your pattern. Go ahead. You give it to me. Minus 4x squared. Okay, go ahead.
Plus 21.
All right.
Minus 6x.
Okay. Now, what you want to do over here is do that first.
So
don't turn these two negative signs into a plus sign yet, because this -2 has to multiply both of these terms over here. So I'm going to still put this negative sign there, and then I'm going to put parentheses around it. Now distribute the -2. What do you get?
-2x squared minus 6x.
Okay. And now I can get rid of these parentheses by turning that into pluses. Okay? Now, simplify. How many x squareds do we have?
-2x squared.
Okay, how many x's do we have? And sometimes it's helpful, I like to do that so I don't forget one.
Right. Looks like it'd just be 14x.
Okay, plus 14x. And how many numbers?
Plus 21.
Okay. And the denominator is still 7 minus 2x squared. And there really is no point in expanding this.
Right.
And that's your answer. And like I said, once you remember the quotient rule, in other words, begins with the bottom and ends with the bottom squared, and you can always plug it in, then everything just becomes hard algebra. And even though this problem didn't illustrate my other point, a lot of times, let's say I did end up with a 7 minus 2x over here. Okay? Now notice that I can factor out that 7 minus 2x and then cancel it with one of them that's in the denominator.
Right.
So, and surprisingly enough, there's a lot of functions where you can do that after using the quotient rule, particularly when you're taking the second derivative. You've done second derivatives, haven't you?
A little bit, yeah.
Second derivatives are merely the derivative of the first derivative.
Right.
In other words, if this is my first derivative, which it is, then if I want to take the second derivative, I just take the derivative of this, applying the quotient rule again. And this time I will end up with 7 minus 2x in two places in the numerator and still in the denominator. So I will be able to factor out a 7 minus 2x and cancel it with, I'm going to have 4 of them. Because when I take the second derivative of it, I got to square that. So it's 7 minus 2x to the 4th power. Then I'll have one in the numerator that I'll be able to cancel, and this will turn into 7 minus 2x cubed, and I'll lose the one in the numerator. So this thing where you factor out the numerator and cancel it with the denominator usually always happens on when you're doing the second derivative, applying the quotient rule a second time. 3 minutes. Let me give you 2 quick questions on the chain rule. If you can figure these out, you'll have the chain rule made. These are not the same function. This means sine x times sine x. This means sine of x squared.
Okay.
What's the inside and the top?
X.
No. The reason I say no is because the way to figure it out is if that were the inside, I would have to write it like that. I don't know how to differentiate that any easier.
Right.
That didn't help. Making u x didn't help. But notice if I make u sine of x, now what I have is u squared. I can differentiate u squared. So that's the way I'm going to go. And then the derivative of the outside would be 2u times the derivative of the inside, which is cosine of x. So my final answer would be sine x cosine x. That's how I differentiate sine squared of x.
Okay.
Take the derivative of the outside times the derivative of the inside. But you've got to know what the inside is. Now, on the second problem, what would u be? Remember, once you substitute it, you got to know how to differentiate that thing.
Bx squared, right?
Yeah, because now I'm looking at sine of u, and I can differentiate that. That's cosine of u times 2x, the derivative of the inside. And I can think of no functions where it's harder to teach somebody the difference, how to get the inside, than these two. These two are the best two. They're almost the hardest. Tell me what the inside of this is.
E?
No, E is a number. E is a constant. When you make your inside, it's always going to contain the variable, for one thing. Because the inside has to be a function of x. That's a function of x, that's a function of x. So the inside here would be 3x. U equals 3x, because then what you're doing is differentiating e to the u. Well, I know what the derivative of that is. It's e to the u. So what you make your inside, using this u notation, you have to be able to differentiate that once you've plugged it in. You don't always have to use u, and that's why they've come up with a real simple rule that it's the derivative of the outside times the derivative of the inside. So you can get away without using u, but yet on the tougher ones, the u substitution definitely helps. It helps you figure out what the inside should be. It's not always perfectly clear what the inside should be. All right. I am going to let you go. Nice working with you again. I'm glad you're taking calculus. There's nothing I'd rather tutor. I wish every student I had was a calculus student. It's just so much more fun. Just because calculus is very challenging. It really is.
Definitely,
yeah. Yeah, it's probably the hardest thing you've ever taken, except for maybe physics.
Yeah, it's close.
Yeah, it is. When I got to college, I found physics to be harder than math. And that's why I started out as a physics major at Mines. And I switched to math after I didn't really have the talent for physics that one needs. And I did have it for math. So.
Well, thanks so much.
Talk to you next time.
All right.
All right. Bye-bye.
Have a good evening.